In this example, I want to do a two-stage multidimensional problem that has so much to teach us. So it's deflection of a charged particle. And so we start out with a charged particle with some speed v. And it enters in a region of two plates. And these plates have a length we'll call p, at which the particle is accelerated while it's in this region. It's the vertical direction here on the screen. After which it will emerge with some velocity in that direction, and then eventually that will show up on a screen some distance away. And so let's call the distance between the output of the plates to the screen, we'll call that Q. And the distance that it is deflected, we'll call here this L. And so we want to know what sort of acceleration we will need to apply to the particle such that it will deflect an amount L. You might think this might be a charged particle, say a medical device, where you're trying to arrange a stream of charged particles to direct it to a certain location. Old cathode ray tubes, things of that nature. Okay, so what sort of parameters are we talking about here? And so just to throw out some speeds, this is about 1/10 of the speed of light. We'll give it 5 times, not 1/10, 100th, like 1% of the speed of light, 5 times 10 to the 6. The plates themselves, P is only about 5 centimeters in length, so that's 0.05 meters. We're going to say the distance that it exits to the screen is more like 1.5 meters. And we want to deflect it something around 2 centimeters. So that gives us 0.02 meters. So that sort of sets the scale of what's going on. The V is very fast, about 100th of the speed of light. This region, P, we can see that P is much, much smaller than Q. The distance in the plates is much longer. Outside the plates is much longer than the distance within the plates. And so the acceleration acquires some velocity here within the plates. It's also going to acquire some deflection within the plates. And so there's a deflection within the plates, there's a deflection out of the plates. We have two regions of constant acceleration that we have to separate out, as well as two dimensions. This could be a very complicated problem. And so the way I'm going to, sort of in the brainstorming session, one of the things I'm going to do is introduce you to a very powerful technique. This is the sort of technique that separates exceptional problem solvers from those that are not. What I'm going to do is I'm going to solve a different problem than the one that is asked. This problem is really complicated, and I'm afraid I'm going to get bogged down in all sorts of terms and uncertain where to go. So instead of trying to tackle that problem directly, I'm going to solve a simplified version of this problem, one that I'm more confident that I can solve, and in doing so I'll get some practice as well as hopefully gain some insight into the more complicated problem. So how am I going to create a new problem that has those characteristics? What I'm going to do is I'm going to say, let's assume there's no deflection inside the plates. So I have two regions of space, sort of inside the plates and then outside. And inside the plates, it's going to acquire some velocity. But let's assume for a moment that it acquires no deflection, so that when it reaches the output of the plates, it hasn't changed its vertical in this way direction at all. So let's get a coordinate system here. I'm going to call x along the beam direction, and I'm going to call y the direction of the deflection. The other thing I'm assuming here, of course, is that gravity has no effect, and that is probably a very accurate approximation, but we could look at that at the end. But at the moment, I'm going to, so that's the first assumption, I'm going to ignore gravity, but also I'm going to assume that there's no deflection, and that I think should simplify my my problem significantly. Okay, so at the end, at the exit, it's going to have some velocity vector, and that velocity vector has its initial velocity in the in the x direction, plus some new velocity it has acquired in the j direction. Okay, so we're going to look at this in stages, and so let's look at the exit stage first. This is after it has come out of the plates. So why would I do that? Why would I look at the exit stage first? Well, this is uniform motion. There's no... I'm ignoring gravity. So this should be particularly simple. There's no acceleration in either dimension once it leaves the plates. So let's look at our two dimensions. I'm going to put my coordinate system right at the exit. That's my origin. So my initial x position is 0. My final x position is when it gets to the screen, so that's a distance of q from my origin where it exits. And then my final velocity is equal to v naught, is equal to my initial velocity. There's no acceleration here, uniform motion. So in the y direction, that's 0 initially. My final y is the deflection L, and my final Vy, I don't know what that is. That's what I'm going to acquire in the first stage. Okay, so what does this? How does this link now? My unknown, which is L, with what I want, with my known, which is Q and V naught and V sub y. Well, I know that uniform motion, so the distance in the x dimension is equal to the velocity in the x dimension times time. Initial x position is 0. And my final position in the y dimension is equal to my velocity in the y dimension times time. And so t is equal to q over v naught, substitute into there, and my deflection is equal to the distance q vy over v naught. And so this is particularly easy. Now I have a expression for my deflection in terms of the velocity that I give it inside the deflection region. Before I go on, I want to show you another way to do this. So if I go up here and I look at this, I said that once it exits here, it has a velocity along this orange line and a deflection. So if I look at this on my picture in terms of my position vector, if I call this angle alpha, just from the triangle here in my diagram, I know that tangent of alpha is equal to L divided by Q. That's just from trigonometry. But since this is uniform motion, I know that my velocity vector is pointing along this same line. And given my coordinate system as I've defined it here, I can look in what I'll call velocity space, say, and my velocity vector diagram, tangent of alpha is equal to the y component of the velocity divided by the x component of the velocity, which is v naught. Well, alpha is the same in both of these relationships. So that gives us that L over Q is equal to Vy over V naught, or L is equal to Q Vy over V naught. That agrees. And so again, here's sort of another way to look at the problem, another representation for the problem. In fact, I would say sort of the pictorial representation of our problem gave us a solution just as easy as the mathematical representation. But in reality, in real life, when you're focusing on problems, you end up doing a problem every possible way you can. That's one of the most important ways that you check to make sure that you didn't make a mistake. So I'm now very confident that I have the correct expression for what's happening at the exit stage. Well, now let's look at do the same thing between the plates. So now let's look at between plates. So I'll blow it up here. So this is some length P. And remember, I'm assuming it doesn't in fact deflect at all, that it only acquires a velocity. So in this case, well, in the x dimension, I have exactly what I had before. It travels. If I say this is here's plus x and plus y, and so in the x dimension, it travels a distance p is equal to its x dimension speed, which is v naught times the time. Now this t is now the time within the plates. Now in the same time, it will acquire a vertical speed, vy, which is equal to its initial, vy naught, which we said was 0, plus the acceleration that I put on the plates, times the time within the plates. So again, the time within the plates is simply the distance in the x direction divided by the x velocity. That allows me to substitute into here, and I have the final velocity is equal to the acceleration that I put on the plates, that I allow the plates to create, times p, the distance in the plates, divided by v naught. Well, now I can substitute that into here, and I have an expression for the deflection L in terms of the acceleration that I put on the plates. Q over v naught times the length of the plates, p over v naught, and finally L, the deflection, Q times P, the length of the plates and the length to the screen, over the x speed squared times A. And so if we want to turn that around, I guess if we want to find A, then in terms of the other parameters, what sort of acceleration would I need for a set length, then we have squared over QP times L. All right. So if I, in fact, put in the numbers that I have here, I will get that an acceleration is given by 20 times 10 to the 12 meters per second squared. That's the sort of acceleration I would need to deflect the charged particle so that the deflection at the screen would be 2 centimeters. This is about 6.7 times 10 to the 12 meters per second squared. So the first thing we see already is that it certainly was a good approximation to eliminate gravity. I mean, the gravitational acceleration is so completely negligible compared to this acceleration that it was completely appropriate to ignore gravity. So that's good. But it's not clear yet how important it was to ignore the deflection that the particle had while it was in the plates. It was deflected some amount d before it exited, and that changes then the relationship between these two stages of the problem. But now that I've solved this problem and I've got an answer for this one, I feel confident that I can take on the more complicated problem now and be able to solve it. We'll do that in the next video.